element of the program for today, other than the reception, of course. There is a reception after this, but you have to sit through the next speaker. Every year when we organize our Digital Futures Conference, we would like to invite at least one speaker who could bring us out of space, somewhere out there that is very innovative, something that we normally don't think about, and just shake us up a little bit. This year, I think hopefully it will not be a disappointment. So Professor Min-Jun Kim is a good friend of mine. He and I went to the same high school. He's much older than me. No, he's younger than me. But I met him actually when I was in Philadelphia. So some through social functions. Currently, he's the Robert C. Womack Endowed Chair Professor of Engineering at the Department of Mechanical Engineering at Southern Methodist University in Texas, Dallas. He received his BS and MS degree in mechanical engineering from Yonsei University and Texas A&M. And then he did his PhD at Brown. And then he did his postdoc at Harvard. And then he went to Drexel in 2006. And within 10 years, he became full prof, which was the record in the history of Drexel University, according to him. I have to trust that. But his work spans multiple disciplines. Mechanical engineering, obviously, is his area, but AI, biology, medicine, and a bunch of other things. Quite difficult to pin him down as like this is what he does, because he does a lot of really interesting things. But at its core, his work is in the nano, small, invisible robots using a magnetic field or something like that. That's what he does. So he's going to talk about some of his latest work with the title of Reconfigurable Modular Microbotics of Self-Assembling and Additive Manufacturing. So with that, Dr. Kim, the stage is yours.
Many thanks for the nice introduction. And it's my great pleasure first to enjoy autumn colors. So it has been more than 6 years since I relocated in the Dallas. So I never ever seen that kind of colorful the trees in Dallas. So, and the double pleasure to introduce my ongoing research. This is my third time to the visit case, but both the last twice, the visits was in May. So one for another the digital forum, and the other for it's kind of the departmental seminar at the medical school. So at that time, I introduced my small-scale robot for biomedical application, especially drug deliveries and the medical imaging and minimally invasive surgical procedures. But today's talk is mainly focused on the manufacturing. So as you know, many of you guys are familiar with micro-nano fabrication, especially for the building of the small the structure, especially for the semiconductor industrial the stuff. And also these the manufacturing fully based on the top-down method, right? But this process simply consists of two kinds of process, actually three. So number one is deposition, number two is etching, and the number three is bonding, right? But deposition and etching, we just create the layer by the layer structure, and then we introduce photoresist, and then we shine specific wavelengths of the light, and then we create the pattern, and we introduce the etchant, and then we just lay off the certain the layer, and then eventually we create the 2D the structure, and eventually the 3D structure. And I believe you guys are also familiar with the additive manufacturing, for example, bioprinting and the 3D printing, and depending on the materials, there are the metal, the 3D printer and polymer 3D printers, and all this printer covers Meso-scale and the Macroscale, right? Yeah. So today I'm especially introduce one of small scale robotics, that is the modular robotics, and then try to think of a new way to the manufacture a small scale the structure. So first, let me introduce the definition of modular reconfigurable robot. So modular reconfigurable robot systems are made up of the many repeated the modules that can be rearranged or can rearrange themselves into the different configurations depending on the task the robot is to solve at the time. Okay, so how we can utilize this modular reconfigurable robot? Eventually, we can achieve assembling that is related to docking structure to the structure, and also reassembling. So we separate the docked structure, and then eventually we can also reassemble those structure to have different patterns. So there are the couple of the macroscopic modular reconfigurable robot. Probably you are not familiar with this kind of the robot. So but you are familiar with this kind of sci-fi movies, right? So the left side is a Transformers, and right side is Big Hero 6. You have kids, I fully encourage you introduce this Big Hero 6, because this movie covers all kinds of robotics. So the soft robot and micro robot and the modular robot and all kinds of robot, and even wearable robot. Okay, yeah. So if you take a look at this the video clip, you can definitely conceptually understand how modular robot build up certain structure and also reassemble and then reconfigure certain the structure we desire, right? Yeah. So the people actually worked on this field the more than 2 decades, but they mainly focused on the macroscopic the modular robot. So things like this. So M-box and the FreeSN and this kind of the robot assemble, disassemble, and then the creator new the structure. However, all these are the macroscopic structure. For example, that M-box is about the 20 cm by the 20 cm by the 20 centimeter. Okay, and then all actuators and sensors are embedded into that cube, and then also the battery is also embedded. So then we just the program, and then this guy is the self-actuated, and then the creators a certain pattern. But as you see, assembling, disassembling, it takes time, but conceptually very important. The tasks could be achieved, right? So this kind of the small the boxes could be configured to the form like the transformer, like the big robot. Okay, so my idea was inspired by actually transformers. By the way, do you know any kinds of transformer in nature? So I'm mainly working on the small scale world and the micro scale and the nano scale. So the micro scale I'm utilizing. So at the beginning of my the research at the Drexel, I fully utilize bacteria. These guys are living in your gut, right? So most of you guys are scared of the bacteria, but you should know 20% of the bacteria biologically hazardous, but 80% of the bacteria, okay. You enjoy what? Wine? That is based on what? Fermentations, right? But 20% is very harmful, such as Serratia and Salmonella and all these kind of things, right? But these guys are well swimming biologically fluidic environment, that is a non-Newtonian fluid environment. So my study was the fully understanding the swimming mechanics. But interestingly, these guys, the living environment goes worse and worse, and this guy just try to save the energy, and then they just create a swarmer. Okay, and then eventually further evolve to form the multicellular left, and then environment goes back to normal, and then these guys de-differentiate, and the multicellular left to be the swarmer to be the planktonic state of the bacteria. So these guys naturally transform the body. Okay, so I thought that because I'm working on the drug delivery system, these days my research group is fully utilize the virus like the nanoparticle. So because the virus is the best of the best to embed it into the target cell and also the target the organism. But the question is how to control this guy, right? So for example, in this lecture room, there are about 50 people. I just suddenly say, hey guys, turn left. How many of you guys turn right? It's 20%, okay? So there are that kind of the tolerance. So that is the biological system. But I briefly introduced nanofabrication and the microfabrication, right? So these days, the Samsung and also the Intel and the other TSMC, they just challenging 5 nano, the manufacturing, the technology, right? So the best thing is to minimize a certain tolerance and then to create the certain structure we desire, right? So we consider all that kind of a thing and then figure out how to build up the Meso-scale modular robot. So about 10 years ago, so CMU, there is the Metin Cities group actually to build up like a dice like the structure, and then the magnet embedded inside of the cube, and then they just manually assemble, disassemble this guy. But there was no motion planner. So assemble, disassemble was unpredictable, and then accidentally create the certain the 2D, sometimes the 3D structures. Okay, so this is a kind of the modular robot at the beginning the stage, but magnetic the motion eventually fully controllable by the external the magnetic field controller, and then depending on our engineering design, we can also overcome couple of the obstacles to move forward this kind of the modular micro robotics for self-assembling and the disassembling and the reassembling to the build up the specific 2D and the 3D the structure. So our idea was utilizing this the small scale the modular robotics, and then to try to build up new types of the manufacturing tool. So simply speaking, we have a small box, and then we manage the magnetic field XYG. And then we just introduce couple of the magnet, and then as you see in the transformer, right? So this the dice is assemble, disassemble, 2D and the 3D, and we have multiple boxes, and then individual box create its own the pattern, and then all this pattern also to reassemble, and then we create the bigger structure in 2D and 3D, and then we just scale down this kind of the principle to micro and the nano scale. We eventually create the mask-free the lithography the technique. So for example, here is certain pattern, creator 20 and T and this kind of a structure, and then we irradiate UV, and then we just take out this structure, so we have the 2D pattern. Okay, so this is the kind of the mask-free photo the lithography. And also you will see that these guys also assemble, and interestingly assembled structure could be playing a role in mobile robot, and then they can also create the different the types of locomotive mode, and then they can also deliver certain man-made object from the A to B, and then we can also introduce this kind of a small-scale robot into the body. For example, scaffold created by the hydrogel or other the bond material, right? And then we just build up this kind of the technology, and then we create a biodegradable and the biocompatible the 3D structure, and then using the tissue regeneration engineering, and then this kind of the technology could be deployed into the biomedical field. So we design small cube, and then these the two parts the printed by the 3D the printer, and then key is to how to organize the number of the magnet inside of this the 3D printed mold. So in this case we create two different cube. One is blue and the other is red, and then there are 8 the permanent magnets embedded, and the blue so this face has the south pole, and the red this face has the 2 the north pole, and then eventually they close each other, and then they create the bond, and then we also introduce a certain the torque, and then this guy just disassemble. Okay. And then we introduce this the small cube inside of the nested 3-axial Helmholtz configuration. There are only 2 kinds of the magnetic configuration. Number one is Helmholtz, the other is the Maxwell. So if you just take MRI imaging, that is fully based on the Maxwell. So there is the magnetic gradient. So magnetic gradients based control is simple, just the pulling and pushing. Okay, so when we deployed this kind of a small magnet cube inside of the MRI system, we can create 2 motion. So moving forward, moving backward, but cannot control the direction, turn left, turn right. So Helmholtz configuration enabled us to also create a rotational magnetic field. And then so both configuration also have the different magnetic field. So this is also directly related to the radiation, things like that. So basically, this guy was the build-up for the animal experiment. So we usually inject small the nanoparticle into the animal model, and then we try to control their motion, and then utilize this system for specific targeted drug delivery system. So then we just introduce workspace. So workspace is usually 15 by the 12 by the 8 centimeter the cube. So within the workspace, we can create a uniform magnetic field. Okay, and then we introduce this cube, and then we control this guy, and then we assemble disassemble this the small the cube. So so here is the one example. So I like to navigate this cube from A starting point to the target point. This guy should create a certain locomotive mode. So we just build up to 2 different the motion mode. One is the pivot walking, the other is rolling. Rolling is simple, right? And then there is another the motion mode, that is tumbling. So for example, this kind of the rod-like structure create a motion like this. This is rolling, but like this is tumbling. Okay, and then we can also create the wiggling, right? And then pivot walking is the things like this. Okay, so we basically create translation of the motion, and then we test this kind of individual the modular unit, and then we also evaluate the speed, and then the magnetic property under the different the magnetic field. Eventually, that information would be very important for the disassembly. Okay, so then what we did, we just create a combination of the serial self-assembly and parallel the self-assembly. Okay, so as you see, the serial self-assembly is very simple. We have two the cube, right? So this arrow also shows it's kind of the direction of the magnetic field, and then the creator the serial, and then parallel is the things like that, and then at the beginning they have their own position, and then we just control this guy using the pivot walking, and then utilize its the boundary, okay, and then create a I shape, and first the I shape, and then this guy just reassemble, and then create the L shape. But this manipulation is fully based on the manual control. So we try to control this guy using the programs, and then we also introduce motion planner and the motion trackers, and eventually introduce motion the algorithm, and then we just predict all kinds of the possible assembles, and then disassemble, and then create different the pattern. So when we introduce the 6 and 8 and cubes, and then we can create the two identical shape and also two non-identical shape, and then eventually we can also create a large assemble from two the non-identical the shape. All these the assembles based on the pivot the walking. And of course, assemble the structure could be also reassemble, and then the further assemble to form another the 2D the structure. Okay. So this is swarm control under the magnetic the field, also the fully predictable using the motion the planner. So we created the motion planner, and then we also validate that motion planner with the hardware the experiment. But as you see, motion planner full based on pulling and pushing. It was very difficult to introduce a pivot like walking into the motion planner, but we also reflect certain the error rate into the hardware the experiment, and then we do the experiment to create this kind of the pattern. Oops. So self-assembly algorithm, the very simple. Okay. So simply there is a P, S, R, L. So P, this cube, the move left, and S move right, and R is counterclockwise. No. So this is right. So this is clockwise rotation, and L is counterclockwise rotation. So using this kind of symbols, we can also digitalize our control the algorithm to produce the different patterns. And then we also figure out certain displacements that are made by the different the sizes of modular cube. So when we use 10 millimeter edge cube, they have the different displacements per the cycle. And then structure is smaller and smaller. They have the different displacement. Okay, so depending on the displacements, we also have to think of certain the manufacturing time, because the workspace is simply say the 10 by the 10 the centimeter square, and then small one, it takes time to reach the boundary, right? Yeah. And then we run the motion the planner, and then when we introduce 4 cube, 2 blue and 2 red, we definitely figure out how many the reachable the polyominoes could be created. So in this specific the pattern, so using the magnetic field, 8 steps the left, and then 1 counterclockwise rotation, and 7 also move the left, and then we create this kind of the pattern. Okay, so we just program all this kind of a thing, and then we create the certain the pattern. So right after create the square pattern, we also manipulate the motion using different the motion mode. In this specific case, we can introduce say the rolling motion, and another is the pivot walking, and then this guy just moving around inside of the walk the space. Okay. Oops. Yeah. So in this case, we introduce the 5 different the cube. So the 3 blue and 2 the red, and then using the motion planner, we can predict how many the reachable the structure could be developed, and all these symbols related to how to build up that structure using the direction of the magnetic field. Okay. Yeah. So this is 10 millimeter the cube. This is a 2.8 the millimeter the cube. So this day the smallest the permanent magnet the commercially available, its size is about 500 the micrometer. So that permanent magnet could be further scaled down. Our the cube could be also the smaller and the smaller. So as you see, this cube, its size is about 5 times smaller than this guy, and then it takes the longer time for assemble, disassemble. So in order to shorten that the manufacturing the processes, we can create the smaller workspace, and then we can overcome that situation. Okay, and also the bigger one has the more the friction, right? So controllability would be much better than the smaller one. We also consider that kind of a thing. So in order to overcome that extra the energy related to the surface energy, this day we just deploy this small the cube inside of the water, and then we try to manipulate the 2D structure and the 3D structure. So basically using the motion planner, we try to build up all reachable structure. So I, the T, and the G shape, and also T shape. And then this guy could be also right after assembling, they just disassemble and then create the new pattern using reassembling. Okay. So far you saw 2D assembly, and the 3D assembly is the more challenging. So we also introduce the motion planner, and depending on the number of the modular the cube, and we also to try to figure out how many the reachable 3D structure that could be produced by this technology. And also especially for the 3D patterning, we have to also to redesign location of the magnet embedded inside of the cube, and then also we control the number of cube, especially to the control disassembly the process. So basically, in this case, we have one blue and two red, and then we create the 25 the different 2D and the 3D pattern, and one red and one blue, one green. So red, blue, green, as you see over here, they have the different number of the magnet, and also their the position the inside of the cube. Okay, and then we just predict all this kind of the pattern, and then experimentally validate this motion planner, and you can see over here things like this. So at the beginning we have the two the blue and two red and two green and two yellow. They have the different the magnet the inside, and also the different position. And create first the 2D structure, and we also introduce pivot working, and then reassemble and create the former the 3D structure. So so this is the programmer. So we integrate the motion tracker and the motion planner with the motion controller. So in real time, our student can build up the specific pattern in 2D and the 3D, and also these days we can also introduce the deep learning and the machine learning, and then we also minimize a certain error in the building of the specific 2D and the 3D the pattern. Okay. And we further scale down and the microscale. So individual cube has 900 the micrometer the edge length, because of the single cylindrical the magnet has 250 micrometer in diameter. But as you see, controllability quite interesting. See. Same size and same number of the magnet, but under the uniform magnetic field, there the displacements is quite different, right? So this is directly related to controllability. So if we cannot manage that controllability, eventually assembled structure would be the different, okay? And also the disassembly the processes would be the more the challenging to create the different the pattern. So we minimize this kind of error factor. We also rethink of our material, and then we just build up kind of the soft robot. Okay, so as you see, so the first generation of the modular the micro robot, they has the number of the magnet inside, and then their the position quite complicated, right? So engineering design the principle is the simpler the better, right? So we create just the cube using the 3D printer, and then we create the cavity inside of the cube, and then we introduce not a cylindrical the magnet, but spherical the magnet. When we use a spherical magnet, we have a lot of the degree of the freedom for the scalability. So you may know there is an oxide nanoparticle. So its diameter is 50 nanometer, And this oxide nanoparticle is the biocompatible and the biodegradable. And all this kind of permanent magnet commercially available, and its the diameter is also in a range of a couple of the nanometer to even the millimeter scale. Okay, and also there are paramagnetic and the photomagnetic. Photomagnetic, the metal is inherently magnet, but a paramagnet, depending on the magnetization, we can just endow certain magnetic property onto the particle. So we can also have also a lot of the degree of the freedom to utilize the many different materials. Okay, and then in this case, magnet could be fully rotating inside of the cavity. So cube itself cannot movable, cannot be movable. However, this guy creator assembled the structure using two individual cube. This guy also the creator pivot working. Okay. So at the beginning we have two assembled the cuboid, and then this guy actually tumble, and then assemble the other cube, and then propagate to the form I shape, and then change its direction, and then this guy just navigate through the major like structure. Okay, and the other case, and also it also to overcome static obstacle, like that kind of the locomotion. And this the major structure has a small the tunnel. So assemble the two cuboid, the tumble, and then they determine the turn left or the right, and then assemble the another structure, and then make it longer and longer, and then also to overcome static obstacles. But things like that. And the last one, you can see the tumbling to overcome that static obstacle. Okay, so all these the small scale robot could be used for assemble, disassemble, and reassemble the process to create the 2D and 3D structure. Now let me introduce new concept of micro the manufacturing. So we are using, as I said, the soft robot. This soft robot looks like a BB-8 droid in the Star Wars. Okay, so there are the snowman the robot, right? And then this guy just moving the things like that. So idea is things like this. So let's recall how to produce the automobile system. So there are a lot of the machinery part, right? And then the convey system, and then assemble the process could be created, right? And then we just miniaturize this kind of manufacturing the processes into the microfluidic network. Okay, and then we manage small the machinery part. Okay, and then this machinery part the flow onto certain the assembly area, and then to create a certain pattern, and we have the final product. And all this kind of the small scale factory system the parallelly rearrange it, and again individual the final product could be reassembled, right? And then eventually we can also create the final the product. Okay, so we address it as a biofactory on a chip. So simply saying there is the 4-inch wafer, and then we introduce a different small soft robot, and then eventually we create the 2D scaffold or the 3D scaffold the structure. That is ultimate goal. So idea is very simple. So polyominoes is a 3D geometric the figure formed by the joining squared the edge to edge. So using external magnetic field, we just push that the square into the initial structure, and then we just pull push, and then rotate counterclockwise and clockwise, right? Using the obstacle. Eventually, we create this kind of the pattern. Yeah. So the model is very simple. So this black line is obstacle, right? So this small the obstacle play a critical role in the assembling in this process, and then white space is the free space, that is workspace, and then red and blue is the one type, and the other type small cube or the particle. And then we introduce magnetic field down, left, up, right, down, left, up, right? So it's kind of a clockwise the rotation, and then this guy is sequentially move that kind of the magnetic the field direction, right? And then create the certain pattern. So this is the fully based on the particle computation utilizing the obstacles. So let's see what happened. So assembling process sequentially is very simple. The first step is to define the build order, and then second is deconstruct the part. But note that this construction is inverse of deconstruction. And then we just reverse the order of deconstruction to define the build order. And then based on the counterclockwise the rotation of the magnetic field, we can just construct of the factory the layout. So here is a kind of a convey system. So the workspace, and all black is the obstacle, and there is a hopper. Inside the hopper, we just introduce the number of a cube or the particle, and then we just push this guy, the magnetically, and then get into the workspace, and then they assemble all this assembly part, and then we create the final product. So depending on the 2D pattern and the 3D pattern, we can also calculate the size of the factory. So this is the one example of the assembly process using this kind of micro factory on a chip. And blue and red, they have the different the magnetic property. We can control them using the number of the magnet or the number of the magnetic particle. And then using this the black the obstacle boundary, and then we create this kind of the final structure. We just redesign workspace and all this the obstacle, and then we can also create the different the 2D pattern. And this kind of micro factory on a chip is rearranged the vertically, and then we definitely create also another the 3D the structure. It's not working. Okay, so we can, as I said, calculate size of the factory, especially height and the width. And then we just reflect it onto our design of the workspace and obstacle boundary condition. And we like to create this column shape and row shape and zigzag shape. This just shows you all this kind of the plot. So x-axis is the number of tiles, and the y-axis is a factory size. So simply there are the 50 tiles, blue and red. And then eventually we could create a certain this kind of straight form of the structure, and then we also to manipulate that, reassemble, and then create another the structure. Okay. So this shows you the same how to evaluate the size of the factory, and then macroscopically we just introduce the gravity, right? And then we test our operation, the principle, and then we create that kind of the final product. And depending on the number of this kind of the disc-like the magnet inside of a hopper, we create also the number of the final the product. Okay. Yeah. So we try to miniaturize this kind of assembly system in the micro scale. So we try to build up the specific system. So in this case, we don't need the rotational magnetic field. We just simply create the pulling and the pushing. So we just introduce a permanent magnet under the bottom of this the stage, and then using the stepper motor, and then the magnet just move forward and backward, turn left and turn right, and then we create a kind of a rotational the motion. And instead of a small cube, because a cube has a relatively large the space area comparing with the spherical the structure. So spherical structure has the small contact area, so we just minimize the friction. Yeah. So we develop the alginate, the cellular, the micro robot. Alginate is the biocompatible, the biomaterial, and then well used for the tissue engineering. And we introduce oxide, the nanoparticle, iron oxide nanoparticle, and then we definitely introduce many the living cell inside of the alginate, and then this living cell can have its the viability for the couple of weeks. Okay, and then eventually we introduce a specific the agents such as EDTA, and then this membrane the broken, and then inside of the cell could be the released. Yeah. And then using rotational magnetic field, we also control its motion. And then, like a BB-8 droid, it has the rolling motion, like that. Yeah. So DU is the initial of the Drexel University. Yeah. And we introduce this guy into the microfluidic network, and we have the square structure over there. Yeah. Yeah, things like that. Yeah. So this is also the further the develop it to create the 3D the structure. So using the microfluidic network, we developed that kind of a new technology, and using not only the cube but also different shapes of the modular the cube. And we also try to assemble, disassemble 2D and the 3D patterns. And also we parallelly reposition all the assembled process, and then we create a certain the final product. And also final product has also the modular robot. It can be also manipulated by the external magnetic field to navigate the certain the environment. So reassemble robot itself is also the robot. So the conclusion, so inspired by existing the biological the system in nature, advances in the robotics, modular robotics and the micro robotics, and we just further scale down to the nanoscale, and the nano robotics have breached out the limitation to navigate and explore environment at the small scale. And key novelty of this modular robotics is the resulting the structure itself is the robot. And as you see, in combination of motion planner and the tracker and the controller, we can further refine this technology down to the small scale. So eventually we do not need any the photo mask or the chrome mask for the photo the lithography. So we just introduce a specific the number of cubic the modular robot onto that photo lithographic the tool. Depending on our desired pattern, this guy just disassemble to form the 2D the pattern, and then we create a specific pattern on the photo the regist. So I acknowledge my student and my collaborator and funding agency, and I'm happy to take care of your question. Thank you. Yeah.
So if you have any questions, just the microphone, or we might bring any questions from the virtual audience. We have about 10 minutes. We're going to kick it 10 minutes. Any questions? I have a question. How long would it take to see actual application of this? And I can see. I can see potential application. So I can see the potential application in semiconductor manufacturing in a very small scale, bio sort of 3D printing replacement type of situations using this kind of model. What's the time scale? How long would it take for us to actual industrial application?
Okay. So in order to adopt this kind of technology in the semiconductor area, probably it takes about 10 years. Yeah, yeah. Because we are at the beginning the stage, and biological application, clinical trial and the non-clinical trial. So I expect 20 to 30 years. Yeah, things like that. Interestingly, last summer, I also attended the robotics conference, and there was one faculty from School of Nursing, and then Children's Hospital. Small kids are hospitalized and stay in the hospital for at least a couple of months, and some unfortunate the case year by more than 1 year. So she said this kind of application could be good for kids in that kind of children's hospital. So they just figure out certain the simple alphabet, and then they just program A, B, C, and then this guy assemble A and B and C, right? And then that kind of application, I think, within 1 to 2 years. Yeah. So it's fully depending on potential applications. Yeah. Yeah.
We have another.
Yeah, we have a question from one of our online viewers.
Mm-hmm.
Do you use the conductivity of the alginate hydrogel? Do you use a 3D printer for the alginate hydrogel robot?
Mm-hmm. Yes. So either way, we can directly utilize the printer. And another way is we can also create it manually using just the syringe. Yeah. So depending on the size of syringe in diameter, inner diameter, we can also create a different size of alginate particle. But bioprinter is more than $10,000. But syringe, by your hands, just $1, right? And then number of alginate particle, probably same, right? Yeah, so if you just consider also economic cost and blah blah, and then you can choose which one the better for your research. But eventually, if it would be commercialized, we definitely also consider the massive manufacturing. At that stage, we definitely utilize specific nodules and also the bioprinter. Yeah. I introduced, the sci-fi movie, right? So robotics people, these days, commonly talk about, how long it takes to show up, this technology in reality. Everybody know the Terminator 1, 2, 3, right? Yeah. So Terminator 1, film 19, I believe 83 or 84, right? Yeah. And then a couple of the years ago, DARPA, robotics challenge, the tested, I believe, the more than 10, the robotics platform right after, Fukushima, the disaster, right? So before that event, the most of the robotics people thought that the Japan is the leading the country in that robotics field. But right after that, the disaster, any the Japanese robot platform could not be deployed in that harsh environment. Yeah. And then DARPA actually realized that we need definitely specific robot to overcome disastrous event. And then there was a competition, international competition. So at the beginning, Boston Dynamics was the first ranked, and then Japanese company was the second ranked. And then Google and other companies just try the M&A, and then this guy just disappear in that competition. And then this kind of competition continue to the third the challenge mode, things like that. So these days the robot, so especially humanoid robot is the biologically inspired system, right? They can just open the door and close the valve, and all this kind of engineering tasks are available. By the way, are you, so do you know that film, Fantastic Voice? It was a film 1966, but Steven Spielberg remade it in 1986. That was Inner Space. Okay. So there is a space shuttle, and then shine specific light, and then this guy is miniaturized, and then put into our eye, and then this guy navigate through our body, and then kill the cancer. Okay. And then people also asked me, how the nanorobotics could be commercially available in reality? So as I said, Terminator 1 showed up 1984, and then 30 years later, right? It came through in our reality, right? And then Fantastic Voyage, right? 1966. But these days, many small-scale robots are tested in clinical environment. And then this guy tried to kill cancer, and that kind of the purpose, these days ongoing. But clinical test is also must be successfully achieved, and then I believe 10 or 20 years later, you will see that kind of nanorobot for minimally surgical the procedure, especially ocular the surgery, and also the specific surgery.
All right. With that, thank you.
Thank you.
So in order to see the outcome of that research, we have to live much longer than we anticipated. So I don't know whether the alcohols and the snacks that are prepared outside will be helpful to accomplish that goal or not, but at least we could enjoy ourselves for the successful conclusion of day 1 of Digital Futures Conference. So thank you again for your participation, and please enjoy the company, networking opportunities, conversation, whatever you want to do, and we'll see you tomorrow morning. Thank you.